Today we will solve the problem 2.34 of Griffith third edition Introduction to Quantum Mechanics. The problem 2.34 is consider the step potential as given below. That is V of x is equal to 0 when x is less than or equal to 0 and it is equal to V naught when x is greater than 0. This problem consists of four subdivision. First subdivision is calculate the reflection coefficient for the case E is less than V naught. That is, total energy is less than the potential energy, and comment on the answer. Uh, this problem considers the step potential, which is a classic problem in quantum mechanics. First, in case A, the total energy is less than that of the potential energy. So, the reflection coefficient we have to calculate. The wave function is psi of x is equal to A e power ikx plus p e power minus ikx. That is when x is less than or equal to 0. That is, this is basically oscillatory in nature. So this is first one is incident wave. Second one is this second parameter is a reflection. First one is incident, where here k is equal to square root of 2me over h cross square. Naturally, the e is the negative value. So you will get ikx. Then what about x is greater than 0? Then the psi of x is equal to f e power minus kappa x. So this is not a oscillatory one. This is a decaying one. So where k is equal to square root of 2 m v naught minus e over h cross squared. Here v naught minus e is a positive quantity because V naught is higher than E. So naturally this is positive quantity. So there is no imaginary part. It is e power minus kappa x. Now we will see further. Now apply the boundary condition, that is at x is equal to 0. What will happen? You have a wave function psi 1 is must be equal to psi 2. Psi 1 must be equal to psi 2. So we have seen psi 1, that is when x is less than or equal to 0. You will get a e power ikx plus b e power minus ikx. Just now we have seen. And psi 2 is when x is greater than 0. And that case we have seen just now f e power minus kappa x. What will happen at the boundary, that is at x equal to 0, e power 0 is equal to 1. Then this will become a plus b equal to f. Then you have this wave function uh, like psi 1 equal to psi 2. Psi 1 star must be equal to psi 2 star, psi 2 prime. Psi 1 prime, it must be equal to psi 2 prime at the boundary. That is at x equal to 0. That is this wave function and its derivative must be equal at the boundaries. So you take the derivative of this. For first term, you will get ik, that exponential term. Of course, you have a, and here you have minus ik, that term p e power minus ikx. Then if you differentiate this, you will get minus kappa f multiplied by this exponential term. So when x is equal to 0, then the exponential term will become 1. So that means ik a minus ikp must be equal to minus kappa f. But from this equation, from the above equation, you can see f is equal to a plus b. So you replace f as a plus b. So you will get ik a minus ikp, which is equal to kappa a plus b. So which can be rearranged. You group the term containing A as well as term containing P. Terms containing A is here ik minus minus kappa A. When you bring this to the other side, this will become plus kappa. Similarly, for P, if you bring this uh, ik to the other side, ikp, then you will get P ik minus kappa. Then you take the ratio P over A. And then what will happen? P over A is you bring A to the other side, and this terms inside the bracket to the left side. That is ik minus kappa. So P over A is equal to ik plus kappa over ik minus kappa. If we take modulus square, reflectivity is modulus square of the P over modulus square of the A. If we take modulus square, both them will be equal and it will get cancelled. So this will become 1. So we have seen the reflectivity is equal to 1. That means under what condition? When E is less than V naught, that is when total energy is less than the potential energy, it cannot transmit. So only whatever hits at the potential, it will get reflected. So reflectivity is 100%. There is no transmittance. Transmittance is decaying one very low. So here the transmittance is equal to 0. Then we will move on to part B. Now you can calculate the reflection coefficient for the case the total energy is greater than that of the potential energy. Earlier case, the potential energy is greater than that of the total energy. So here K1 is equal to square root of 2 me over h cross squared, and K2, because here the waves moves with a different velocity from when it moves from left to right. Let us say your wave is moving from the left side to right hand side, then the K2 at right hand side is equal to 2m E minus V naught over H cross squared. Earlier case it is V naught minus E, here E minus V naught, because E is greater than V naught. So let us say you have a step potential here. Then when waves start here, when energy is higher than this is V naught. When energy is higher than V naught, so particle will move here. So it will get reflected when particle incident on this side, it will get reflected with the same velocity. But however, it will move to the other side with a different velocity. Both side is a oscillatory one, because uh, the energy is higher than V naught. It has freedom to move both left to right hand side. So right hand side it will get transmitted. So e power uh, e power ik1 x is the incident wave, and the reflected wave is plus p e power minus ik1 x, because it reflects on the same media, so with the same velocity, which is equal to f e power ik2 x. So this is at the right hand side. So this is transmission. When x is equal to 0, this psi1 must be equal to psi2 at the boundary. At the boundary means when x is equal to 0. So when x is equal to 0, you will get a plus p, which is equal to f. I have already defined what is k1 and k2. So now wave function and its derivative must be same. Psi1 prime must be equal to psi2 prime at x is equal to 0. So you differentiate this, you will get ik1 first term, ik1 a e power ik1 x. When you differentiate this, you will get minus ik1 p e power minus ik1 x, which is equal to, if you differentiate this, ik2 f e power minus ik2. So when x is equal to this 0, then this will become I k1a minus I k2p is equal to, because e power 0 is 1, which is equal to I k2f. So here you can take k1a minus k1p, which is equal to k2 multiplied by a plus b, because f is equal to, we got here, f is equal to a plus b. So when you rearrange the term, you group A and B, A to the left hand side and B to the right hand side. You will get A. If you take A outside, you have K1. When you bring this, you will get minus K2. K1 minus K2. Then B, you bring K1 to the other side. You will get P K1 plus K2. So if you take ratio between P and A, so P by A you bring other side and K1 plus K2 to the denominator. So K1 minus K2 is equal to K1 plus K2. So what is the reflectivity? Is modulus square of P over modulus square of A. That is K1 minus K2 over K1 plus K2 modulus square. This is the reflectivity of when E is greater than V naught. Section C is for a potential such this one that does not go back to zero to the right of the barrier. I have explained this already in section P. So when wave goes from here to here, here there is a possibility of reflection, incident wave get reflected. So once it goes to the other side, it will not come back. So there is no reflection, only transmittance. So I have mentioned already this. The transmittance coefficient not simply by the ratio between f squared over a squared, because there is a difference in velocity that you have to keep it in your mind. With the a is the incident amplitude and f is the transmitted amplitude. Because the transmitted wave travels at a different speed, so that E is equal to square root of E minus V naught over E modulus F square over A square. For E is greater than V naught. And also we have to find what is T for E is less than V naught. First case E is greater than V naught. So first you see one by one. The transmission coefficient is equal to the probability of transition multiplied by Vt, velocity of the transmitted light particle, over the probability of incident particle multiplied by the velocity of incident particle. This we got from the equation 2.99. So here, the V naught over Vi, that is transmitted velocity and reflected velocity is equal to the other side we have seen E over E minus V naught to the right side, and the left side it is equal to E. This we got it from, maybe I will explain in a simple manner. So uh, that is, I will erase this. I will explain in a simple manner. What is K1? We have mentioned K1 is equal to square root of 2me over h cross square. And K2, maybe I will write. What is K2? We have seen in section P. K2 is equal to square root of 2me minus V naught over h cross square. Now you take this velocity is the transmitted wave velocity is proportional to k2. If you take the K2 ratio between K2 and K1, 2m over h cross squared will get cancelled. You will get E minus V naught, this one, square root of E minus V naught over E, square root of E. So, what is probability of transmitted wave? Modulus F square. What is the probability of incident wave? That is modulus A square. So, this is the transmittance uh, transmittance of when E is greater than V naught, the first case. What will happen for E is less than V naught? We have seen in section A itself, T is equal to 0 if E is less than V naught. This is, I will use a different color. This is the case when E is greater than V naught, this one, as explained in the problem. This is E is less than V naught. So we have solved section C also. Now we will move to section D. Section D is for E is greater than V naught, calculate the transmission coefficient for step potential and check that T plus R is equal to 1. We have seen in section C that is R is equal to modulus P squared, sorry, section P, R is equal to modulus P squared over modulus A squared, which is equal to K1 minus K2 over K1 plus K2 modulus square. Then transmittance we have seen already, that is modulus F squared over modulus A squared. By definition, it is equal to 4 times K1 K2 over K1 plus K2 whole square. Now you add these two. Then here you will get K1 minus K2 whole square plus 4K1 K2 over K1 K2 whole square. So what about the numerator? A minus P whole square minus 4, sorry, plus 4AB equal to A plus P whole square. So that means here numerator will become K1 plus K2 whole square is equal to K1 plus K2 whole square, which is equal to 1. Hence, we proved that sum of the reflectance and the transmittance is equal to 1. Thank you very much for watching my video and supporting me continuously. Thank you very much.